Hello and welcome to our channel, which is named as Your Diary, to give you a sense of ownership. And we really hope that you're enjoying these lectures on Geography Made Simple optional series, where the main effort is towards making the things as simple as possible and as concretized so that you should not put an extra effort before going to the examination. Our today's topic is this red underlined topic called the fundamentals of geomagnetism. And if you have gone through the previous lectures, we have dealt with factors controlling landform, then endo and exogenetic forces, and then the origin and evolution of Earth's primitive crust, and then we went to physical conditions of Earth interior. And today is the time for fundamental of geomagnetism. So first let me tell you that how we will cover this chapter. First we will see that what is geomagnetism. We'll try to define it. Then we will try to find out the probable causes of geomagnetism. In the third, we will see the evidences that we can find that tells us that there is something called geomagnetism. In the fourth, we will see some associated concepts, like we will see the angle of declination, we will see the dip angle, we will see agonal lines, isoclinal lines, etc. And then in the end we will move to something called paleomagnetism, and then we will give you a synopsis of this particular chapter. But before moving on, like in almost every lecture I try to discuss the philosophy of UPSC, this exam. You know why this particular exam becomes so special and sometimes little difficult? It is because of simple 3 points. What are these 3 points? This is probably one exam which need amalgamation of 3 particular skill. Number 1, gathering of knowledge. You have to have a lot of information in your brain, but the effort does not stop here. You have to internalize those information through a process called linkage. And your effort does not stop even here. Once you have the knowledge, you internalize it, and then you have to have a writing skill using keywords. I told you many times, these keywords make your optional geography paper looks like a geographer's answer. Your polity answer becomes like a political answer because of those particular keywords. Or maybe the answer on international relations becomes so only by the use of certain diplomatic keywords which give you a feel of that particular paper. And probably because of this, the proverb goes like this, that cerebrate to celebrate when it comes to UPSC. You know what is the meaning of cerebrate? Meaning internalize, put it into your cerebrum, into your brain, to celebrate. Okay, with this brief introduction, we'll straight away move to the chapter. And here, before that, to help you cerebrate the different topics of geography optional, let me give you an example. See, we started from factors controlling landform development. What were the factors? Like geologic structure. There would be maybe a weakness in the rock structure. Through particular this weakness, one will go down, other will go up, and a rift valley will form. After geologic structure, we discussed geomorphic processes, where we discussed about plates. And you already know that Earth's crust is subdivided into several plates. Okay? And then we kept on discussing that how the hot lava flow from the deep of the mantle came up and destroyed these primitive plates to give rise to either mountain or the basaltic ocean floor, etc. And then in the end, continents were formed, which were mainly andesitic and granitic in nature. After that, the next chapter leads to physical condition of Earth's interior, where we gave this conical structure and divided into core, mantle, and the crust. Now we are going to geomagnetism, and you will see that how this particular physical structure of the Earth and the trizonal division of the Earth leads to geomagnetism. And once we finish off with the geomagnetism, you will see this particular concept of geomagnetism will lead to many other modern theories like seafloor spreading. We will read plate tectonics theory. We will see continental drift theory. So this is the linkage. Maybe in the future I will not be able to give you the internal linkage of each and every topic because of paucity of time, but always try to find the internal linkage among the subtopics of a chapter. That will help you get the concept in a better manner. So at the very beginning, if I try to define that what is geomagnetism, it is said that in the most simplified version of Earth's interior that I'm going to draw for you, in the most simplified version of the Earth's interior, it is seen that the crust is nothing but made up of Cl, that is silicon and aluminium. Mantle is made up of Sima, that is silicon and magnesium, and the core is made up of Nife, that is nickel and ferrium. Here I've given you the diagram, and you know this differentiation is very well relatable to our P-bag series that we have discussed earlier, that is peridotite, then basalt, then andesitic and granitic, that series where we discussed that while this hot plume of magma was trying to go up, in every differential layer it was leaving behind the heavier material. So you see in core the nickel and ferrum has been left behind and the lighter material probably moved up, and in the next level of differentiation silicon and magnesium were left behind, okay, because magnesium was heavier than aluminium. And then in the next differentiation level, silicon and aluminium, which were the lightest, they stayed in the crust. So that is the way the nickel and ferrum concentrated in the core area, giving core the heavy nature and its ferromagnetic. And in the next they said that the core is not an exact sphere, rather core is like an elongated bar magnet. You see this shape? Hence this formation is related to the Earth's magnetism, which can be felt up to 60,000 kilometers from the Earth's surface. If this is the Earth's surface, then up to 60,000 kilometers in the atmosphere, because in the 60,000 kilometer limit we have a layer called magnetosphere. So up to that limit we feel the Earth's geomagnetic field. Now, as we've already noticed that the core and the mantle are made up of different ferromagnetic rocks and minerals like silicates, olivine, etc. And because of the liquid outer core, we all know that this outer core is liquid in nature. This part is liquid in nature. So because of different minerals in different layers, like here we have Nife, here we have Sima, etc., and because of the liquid outer core, there is a differential motion that generates the magnetic field. This action is somewhat like a self-sustained dynamo. So this is a liquid medium and this is a solid core, elongated in shape, and because Earth rotates around its axis, so there are differential motion between the liquid outer core and the solid inner core, which gives rise to the magnetic field. Now the next natural question comes, okay, we understood that Earth acts as a self-sustained dynamo because of the liquid outer core and the solid inner core and the different minerals. But what is the evidence that we find that yes, Earth is actually a magnet? You know that evidence comes from this factor. The fact that if you hold a magnetic needle or say a compass anywhere on the Earth's surface, that compass will align itself into a particular direction, pointing the direction of north and south magnetic. Now we all know that compass is nothing but a magnet itself. So when the compass's north pole is pointing towards this particular pole, this pole would be the magnetic south pole, because we all know that magnet's north pole will attract the south pole and magnet's south pole will attract the north pole. So this is Earth's actual magnetic south pole and this side is Earth's actual magnetic north pole. Now we will compare and contrast with another diagram. Before that, one more small concept. During our 9th and 10th standard, we all read about magnetic lines of force, which are nothing but imaginary lines of force that exits from the north pole of any bar magnet and enters the south pole of the same bar magnet. So if we draw the magnetic lines of force here, it will be something like this, emanating from the north pole and entering the south pole. But then here comes a fallacy. We see that this is the actual magnetic south pole and this is the actual magnetic north pole. Now let us compare with this right side diagram. If anybody asks us that where is the geographical north pole of the earth, we all show that this is the geographical north pole and this is the geographical south pole, right? But if you contrast with the left side diagram, on the top, this is the south magnetic pole. Hence, to avoid this particular fallacy, conventionally, for all practical purposes, we keep all northern hemispheric poles as north pole. See, the magnetic north pole also, we will move it here. So both the geographical north pole and the magnetic north pole will be on the northern hemisphere, and both the geographical south pole and the magnetic south pole will be in the southern hemisphere. But the original lines of force direction will not change. So just remember this right side diagram and directly draw this in your exam paper. Now, for quite some time I have been using something called geographical north pole here, and I also said that this is the geographical south pole. What is that? Geographical north and south poles are nothing but the meeting point of the Earth's longitudinal lines. You remember this diagram in our geography books? These are the longitudes of the Earth. The point where the longitudes will meet in the north is called the geographical north pole, and where it will meet in the south is called the geographical south pole. Hoping that this concept is clear, now we will move towards certain associated concepts. Like we will try to define what is magnetic declination. I will give it into a separate new diagram. The magnetic declination is nothing but the angle measured between the line joining the geographical north pole and magnetic north pole. So if I draw the diagram, say India is here, and say this is Indore, a point A, a place in Madhya Pradesh. You know, this is, say, let's Indore. The definition is saying that magnetic declination is the angle measured between the line joining geographical north pole and the line joining the magnetic north pole. So for Indore, the declination angle will be this. Let's say this is 30 degree. Okay, so this is the declination angle of Indore. The angle between the line joining geographical north pole with Indore and magnetic north pole with Indore. If we can find another place B whose declination angle is also 30 degree, then the line joining A and B will be called isogonic line. You know, in geography, iso signifies something similar, like isobars, the line joining areas of same pressure. Isobath, the line joining the areas of same depth. Exactly, this is isogonic, line joining the areas of same declination. Similarly, if we find places with zero magnetic declination, then the line joining such places will be called agonic line. These are the definitions you should remember. The next concept is deep angle. Let me explain what is deep angle. Deep angle is the angle subtended between the direction of magnetic lines of force. You remember? These are the imaginary lines of force which will emanate from the north pole of a magnet and will enter into the south pole. So dip angle is the angle between the direction of these magnetic lines of force and the horizontal earth surface at that point. Hence, the dip angle is 90 degree at magnetic north pole and the dip angle is 0 degree at the magnetic equator. Let me explain this with a diagram. So if you try to find the dip at this particular point A, then the dip angle is the angle between the direction of magnetic lines of force and the horizontal earth surface. You see, at this point it is 0 degree, hence it is also called magnetic equator. Now if we go to magnetic north pole, here the direction of these magnetic lines of force is this and the horizontal earth surface is this. So here the angle is 90 degree. That is why this is magnetic north pole, because the compass will be hanging in 90 degree angle over here. Hope you get the concept of magnetic dip angle. Now we will study the shift of magnetic pole, which is a very interesting phenomenon. As we see, during 2001 the north magnetic pole was somewhere here. This place is called, as I've written here, Ellesmere Island. Ellesmere Island is in a Canadian territory. And then slowly you have seen that 2001 onwards the magnetic north pole has shifted continuously westwards towards a Russian Siberian territory. Okay. Scientists have noticed that the speed of this motion of the magnetic north pole is somewhere around 50 to 60 kilometer per year, and this motion is called Chandler motion, Chandler, Chandler motion. Also in this diagram you notice that the magnetic north pole is shifting towards Russian territory, but this portion, this is the geographical north pole. I told you geographical north pole is the confluence of the meridians of the earth. You see the meridians here? So the geographical north pole is always fixed, okay, but the magnetic north pole is shifting. Now if you keep this concept in head, you can also say that the declination of certain places will also change, because declination of a particular place is the angle between the line joining that place with the magnetic north pole and the line joining geographical north pole. So if the magnetic north pole is shifting, so the angle of declination will also shift. We'll try to understand this with an example of Allahabad. So here is the diagram, and this is the magnetic north pole which is shifting, and this is the geographical north pole and geographical south which are fixed. Now say this is the Allahabad. So the declination of Allahabad will be the angle between magnetic north pole and Allahabad and geographical north pole and Allahabad. So this is the declination. Now we have just now noticed that magnetic north pole is shifting westwards or any direction. So the new, if the magnetic north pole is here now, so the new declination will be something like this, which is definitely smaller than the previous angle. So it has been seen that in 1975 the declination of Allahabad was actually 30 minutes west of the geographical north pole, but in 2001, because of the shift of north pole, the new declination became 0 minute, and now presently around 2019 the declination of Allahabad is some amount east. So the declination became 0 from west and now it has moved towards east. Only this much you have to remember. With this we'll move to the next portion, which is the implication of geomagnetism of earth, and there are around 5 to 6 points of the direct implication of geomagnetism you have to remember. See, the first implication is we see aurora borealis or the northern light and aurora australis or the southern light in the northern and southern extremities of the earth. Why does it happen? This happens because the magnetic energy which will interact with the cosmic rays in the ionosphere of Earth will give rise to this kind of beautiful scattered light in the extremities. For example, this diagram, it has been taken in the Canadian territory. See these beautiful lights of green, red, blue and all sorts of spectrum you will see. This cannot be witnessed from the tropical or the equatorial region. We from India will never be able to see this because of the curvature of the Earth. But the extremities people will see this. Aurora borealis in northern hemisphere, aurora australis in the southern hemisphere. Then the next implication is this geomagnetism of Earth and the change in the magnetic poles will influence the migration behavior of animals. There are many sorts of migratory species, some of the birds or maybe the whales, etc. It has been seen scientifically that their migration pattern or the direction of the places change with the change of magnetic poles. Then the third one is that the geomagnetism of the Earth will protect the Earth's atmosphere from the harmful cosmic rays which will come from the other celestial bodies. If you ask why, the cosmic rays will have charges on them, and maybe they'll be positively charged or negatively charged, and the Earth's magnetosphere will repel them. And then the salinity pattern. As the ions of the salt will be either cations or the anions, again the positives and negatives, so that will also be invariably influenced by the geomagnetic field of Earth. That is why in some portion of the ocean will be very much saline and somewhere the water will be less saline. The fifth one is the ocean current and circulation. So as salinity has a bearing on the ocean current, so the geomagnetism will also indirectly influence the ocean current and the circulation. And we all know that the more the salinity, the heavier the water is, so that way the saline water will go down and the less saline water will come to the surface. This way geomagnetism indirectly influences ocean currents. And last but not the least is the mariner's compass, which is also called gyro compass. The gyro compass helps to find the direction to the mariners. When they will be out in the ocean, they will find the northern pole or the southern pole with the help of a compass. So these are the implications or the impacts of geomagnetism. Now we will move to the last topic, which is paleomagnetism, a small topic which will lead to other modern theories of our study. In paleomagnetism, as the name suggests, that paleo means old or remnant, and magnetism. So this in short means old magnetism. Now if we try to define this, the study of paleomagnetism is a subtopic under geomagnetism, and as the name suggests, paleomagnetism means old magnetism. Hence it is a kind of proof or record of past geomagnetic orientation of Earth written on the ocean floor during the past billions of years. So as you've just now seen that the magnetic polarity of the Earth keeps on changing. The magnetic north pole is shifting now from the Canada towards the Siberian territory. So this has happened many times over the past billions of years. Now when the magnetism changes, then the lava eruption, lava will always have ferromagnetic materials, irons, nickel, etc. So they will also keep a record of the then geomagnetic orientation, and this record will be kept in the basaltic ocean floor. This is in short about paleomagnetism. How it happens, I will show you diagrams. Now before that, let us try to explore that how the scientists came to know about paleomagnetism. See, there are several expeditions made in the ocean to discover the ocean floor. One of such expedition was Glomar expedition, if you have heard the name before. Glomar Challenger expedition. This is nothing but a name of a ship. You can see the picture of the ship in Wikipedia. This Glomar Challenger expedition took place in 1968 and it continued for around 15 years. So it got over by 1983. And these ships used sonar, that is the sound wave. They sent sound wave to the various depth of ocean floor to see what kind of ocean floor is where. And after the Glomar Challenger expedition got over, the next one was Lloyd's resolution. And the full form of, and it happened in 1983 and it is still continuing. The full form of JOIDS is Joint Oceanographic Institution for Deep Earth Sampling. Okay. Now what did these expeditions find? They revealed that there are alternating band of basaltic rock. There are alternating band of basaltic rock of reverse polarity. If this is north, it is south, then the polarity reversed. This became south, this became north, this became north, this became south. So this kind of expeditions revealed that there are alternating band of basaltic rock of reverse polarity on either side of the Moor. Moor is a mid-oceanic ridge and it is found in the Atlantic Ocean basin. And the patterns of one side of the Moor is more or less mirror image of the other side. Now let us discuss with the diagram so that you can understand well. So before I move further, let me explain this diagram once again. See, this is the core and these are the mantles. Now you know that the hot lava will flow from the mantle and it will become the diverging arm, which will tear apart this oceanic crust, and some of the lava will come up from here and will spread on the ocean floor. This is the basics of idea. Now you always remember this mid-oceanic ridge is the area from where the new crustal plate will always emerge. We will discuss this in detail in the plate tectonic theory. Now what I want to tell you, that when the hot magma will come up and spread across over the billions of years, this magma, which is made up of ferromagnetic materials, there are iron, there are nickel, there are magnesium. So these metallic minerals will record the Earth's geomagnetic orientation. Say when first magma came out over here, Earth's magnetic orientation was something. Now after another billion of years, some new magma came up and that will record the next type of magnetism, because maybe by then the north and south magnetic poles have changed their location. So you understand, respective lava flow will keep on recording the then geomagnetism of the earth. Now with this explanation, if you look towards this picture, you will understand it better. See, it is the magma which is coming up and this portion is the mid-oceanic ridge. Okay, this is the mid-oceanic ridge. See here, this is the mid-oceanic ridge. Keep this in mind. And this is our picture A, this is B, this is C. So we will start from here. So when the first lava flow occurs, this they have denoted with red one. This is the first lava flow. Let's say this happened some 50 billion years ago. Okay, and that time the magnetic north was here and magnetic south was here. So north was here and south was here. Now in the next diagram you see that this red portion has changed to this place, and in between there is a white magmatic layer denoted by this one. If you see the arrows given over here, this is arrow this side, this arrow is that side, this arrow is this side, this arrow is this side. So if you notice, you will see the magnetic polarity of the earth have changed. Let me explain once again. This is 50 billion years ago. So this red portion of magma had one polarity. I said this is north, this is south, and this white one here has a different polarity. See, this is north and this is south. That will come to know from the magnetic lines of force. It is coming out from here and going in this direction. See, it's coming out from here, going in this direction. So this is north and this is south for the white one, and the red one is absolutely opposite. Now again the red one is here, you see, this is going inside. So this is south pole, this is north pole. And again the next magmatic eruption, it is white, and this is again north pole. So you see, there are alternating bands of different magma, and as these magma plates will shift apart, these alternating bands of magma will keep the record of the geomagnetic orientation. In short, this is paleomagnetism. Now we have to know few names, for example, and yeah, one more thing, they said that this is the more, both sides will have exactly mirror opposite, and that is very natural, because when magmatic eruption occurs, that occurs almost the similar way in both the sides, so it will be mirror image in both sides of more. Now this concept, during 1960, one Princeton University geologist, his name was Harry Hess. He, during 1960s, propounded one idea which was called seafloor spreading. Seafloor spreading was nothing but this. Seafloor is being created at the more, and they are getting sprayed out. See, this arrow is showing that they are getting sprayed out. So Harry Hess in 1960 said that there is some phenomena called seafloor spreading, but it was not conclusively proven that there is something called seafloor spreading, because it was a hypothesis. But in 1963, two scientists whose name were Vine and Matthews, two different, they propounded that yes, there is seafloor spreading phenomena, and which keeps the record of Earth's magnetic polarity within the ferromagnetic basaltic material. So Vine and Matthews found out this reverse polarity of geomagnetism, and they said yes, what Harry Hess said in 1960, that seafloor spreads, now it is conclusively known that seafloor does spread, and the records are kept in basaltic ocean floor. And in the end we will see that paleomagnetism also reveals that there is a symmetrical pattern on either side of the mid-oceanic ridge, as we have seen in the diagram, and upon their dating it was proved that ocean floor was created in the mid-oceanic ridge area, I already explained, and then it is split at half and pushed aside upon plastic asthenosphere. Hence paleomagnetism links many other emerging ideas like continental drift, seafloor spreading, plate tectonics, etc. I hope this concept is clear. Now I will try to give you a synopsis, how to remember all of this. Now it is the time for synopsis, that final 5 points that you should remember about this chapter. See, the first one, you have to define geomagnetism, okay, and make that triangular diagram. You remember core, mantle and crust, but here you only show Ciel as the crust, Sima as the mantle and Nephe as the core. Okay, now when you know that Nephe is at the core, then try to relate this Nephe and other ferromagnetic minerals. I gave examples, you remember, olivine, etc. So you relate Nephe, ferromagnetic mineral, and the liquid outer core and the differential motion between these layers to relate to geomagnetism. Okay, and then say that this is like a dynamo. So up till here we have come to the conclusion that why Earth is a geomagnetic material. Now let us move to the next one. You have to define declination now and deep angle, and the others are the related concepts. Now I forgot to discuss one thing. The places of equal dip, if you join the places of equal dip angle by a line, that line is called isoclinal line. Okay, it's very similar, just like isogonic, it is isoclinal. Add to your note. Then the number 4th, remember Ellesmere to Siberia shift. Okay, you can relate the shift of the northern pole, that is the Earth's magnetic poles are shifting. And last concept is paleomagnetism. Paleomagnetism is related to two geologists, Vine and Matthews, and this paleomagnetism worked as a proof of sea floor spreading by Harry Hess. Thank you. If you like our lecture, please like and share and subscribe.